My dear friends, welcome to Rajashekhar classes on Applied Data Science with Python. This is lecture number 622. In this lecture, I will continue my discussion on ResNets. Before understanding this lecture, I request you to go through my previous lecture, that is lecture number 621. The takeaway one is adding additional or new layers would not hurt performance as regularization will skip over them. That is first takeaway. My second takeaway is if the new layers are useful, even in the presence of regularization, the weights or kernels will be non-zero. So what is happening now? Interesting thing is by adding new layers, your performance will not decrease, isn't it? That's important. By adding new layers, your performance will not decrease, but it could increase slightly. So because of this skip connection, because of this skip connection, is it not skip connection? Just observe this one. So because of this skip connection, you are guaranteed that your performance will not decrease, isn't it? Your performance will not decrease by going from 20 layers to 56 layers. It guarantees that it won't decrease performance because it completely skip over them with simple regularizer like L1 and L2, making all these weights are useless. But if these layers are useful, certainly there will be non-zero weights or non-zero kernels, and your overall performance will improve, isn't it? This is also called identity unit, because if X is the input, just say if X is the what it says, if X is the input, what does identity function of X looks like? Identity function of X, what is identity function? Just let me write like this. What it says, this is identity function, I of X equal to X. Is it something like that? Isn't it? Identity function of X returns X. This is also called identity block, isn't it? Because the X will return at the end of it. This whole thing literally take an identity function because you are inputting X here and you are getting an output X. Just see, for this particular block, what is input here? Here X is input, isn't it? X is input for this block, and what is output? Output is also X, isn't it? Your input is X, and here for this particular block, for this block is like this. Just let me say, what is this? X is your input and you are getting X as an output, isn't it? X here, you are getting an output of X because this whole thing, because this whole block is useless. This whole block is useless. Simple. X, you are giving X input, it is generating X output. That's what it says. What is identity function? I of X equal to X. That's why this whole thing is called identity block, isn't it? This whole thing is called identity block, or you can say residual block. Very simple concept. Now given this block, let's see how the actual structure looks like. Of course there are lots of ResNets, so this is very nice example. This is just say this is your let me show, this is residual block. Let me go to this particular block, what it says. Just say this one. Let me show that one once. Just see this particular, yes, this is so this is very nice example. This is your VGG19. Just see, you have VGG19 here, which has 19 layers. VGG19 means what? It has 19 layers. We have 34 layers. Even you can say, just see, here you have 34 layers, here you have 19 layers, you have here 34 layers residual network. If you observe carefully, VGG19, 34 layer plane and 34 layer residual networks, isn't it? This is how a plane network looks like. I just see 34 layers plane networks. Just if you observe, in 34 layer residual networks, you have just this jump overs, isn't it? Skip connections. You have skip connections for 34 layers residual network. Just see, you have 34 layers residual network, whereas for 34 layers plane networks, you don't have any skip connections, isn't it? Just I request you to go through this paper. We are recording, we are explaining, we are discussing concept from this particular paper, isn't it? Just compare this 34 layers plane network and 34 layer residual network and VDC16. Remember, in a residual network, you are taking the output. Just see, in residual network, you are inputting here. In the case of this, just see here, you have input. For example, here is giving input image. You are inputting here. You need to input. If you go through that particular structure which we discussed, just let me show that particular structure what we are discussing. Just see here. Here, what's happening? You are taking the output here, and you are taking this x is output of ReLU function. You are taking the output here, and you are inputting here. To whom it is you are inputting x? You are inputting to convolution layer. You need to input before ReLU. Just see here. That's what we were discussing. This is my x. You are inputting here. This before ReLU function, isn't it? Remember, you have to input it before ReLU operation. Basically, you are skipping over 2 layers, isn't it? We are skipping over 2 convolution layers. And when you skip over 2 layers, you need to ensure that there is a very important caveat or certain details here. Here is your x that is going in. You have a convolution. Your x is going into a convolution, isn't it? It's going to convolution. You have a ReLU, isn't it? You have a ReLU. You have convolution, and you have a ReLU. Now over skip unit looks like this. While skip, what happens? This x is directly you are sending this x in the context of skip. You are just sending to ReLU, isn't it? Our skip unit looks like this. This is my skip unit, isn't it? Yes. It goes and connects here. You have to ensure that convolution, these 2 convolutions that we have, the output that you get here is what is the output you get here? Just see, here you are getting output x triple dash. You need to ensure that x and x triple dash are of same size through padding and all of those careful things, because if you don't pad, if the size of x triple dash and x are of different sizes, you can't sum them, isn't it? You can't sum them up. So you need to ensure that convolutions that you are performing will guarantee that x dash, x double dash, and x triple dash are of same size. They must be of same size. Otherwise, you can, isn't it? That's what it says. They must be of same size. X dash, x double dash, x triple dash are of same size. If this, let me assume, if this is an image, let me say this is an image of n cross n. If this is an image which is of n cross n, this is also need to be, your output also need to be, this is also need to be an image of size n cross n. This is also need to be an image of n cross n. If this particular one is image of n cross n, this needs to be image of n cross n. If x is a vector of d dimensions, let me say, if your x is a vector of d dimensions, then x triple dash is also a vector of d dimensions, isn't it? If your x is an image of n cross n, your x triple dash is an image of n cross n. If x is a vector of d dimensions, your x triple dash is also vector of d dimensions. That is important, which means you need to do padding carefully. This is how residual network works. Let's assume these 2 layers are, let me assume these 2 layers are useless. Let's assume these 2 layers are useless. What would happen? Would just get skip connection here, and all these weights are 0. through regularization, isn't it? In this paper, instead of just defining single network, one network, they define lots of networks. You have ResNet 18 layer ResNet 34 layers ResNet 50 layer, ResNet 50 layers, ResNet 101, ResNet 152. You can see, I request you to go through this paper. You can find nice explanation for this ResNets. They have multiple ResNets, isn't it? If you observe, these two plots are very important. An 18 layers plane network is having lower error than 34 layers plane network, but 34 layers REST network has lower error than 18 layer residual network. This is the right expectation. Residual networks are becoming extremely popular today. Again, there are more variations, like this is one form of identity. Just see here, there are variations. This is one form of identity. There is a other form of, this is another form of identity, isn't it? We are experimented with lots of variations. In Keras, what you have here is, so this is Keras implementation. Just see, this is Keras implementation. This is for ResNet 50. Just see, and this is from GitHub. We will provide this link in description section of this video. This is ResNet 50 ResNet 50. They implemented ResNet 50. You have bunch of identity blocks. Just see, you have identity block, convolution block, identity block. Just it's a easy and simple code. You can go through it. The code here is shown how the identity blocks looks like internally. Even you can check. You just go to this particular GitHub URL and you can check this code. They implemented nicely. You have con 2D. Just if you observe this, just see, you have convolution 2D, all these things, con 2D, batch normalization, layers.con 2D. Just see, layers.activation, layers.add. Yeah, at the end of the day, you are summing up them, isn't it? Layers.add, all these things. There is layers.add. This is extremely important. This is that's what we were saying. At the end of this block, what you have to do, you have this residual block. This is my x, and you are getting here, you are summing up, isn't it? Just you are summing up. That's what it says. It says layers.add, isn't it? Layers.add shortcut, isn't it? This is shortcut, this skip connection. Keras has again very nice implementation of ResNet 15. I request you to go through this lecture. If you have any difficulty, please keep a comment. Thank you very much.